So next we're going to ask ourselves, how does Gauss's law to apply to different situations? So I want to look at a line of charge. So let's draw a line of charge here, and we'll say it's an infinite line. We'll deal with finite lines in a different video. We won't be able to use Gauss's law for those easily. So this is going to go infinitely in both directions, so I'll just throw some arrows at the end. And talking about the total charge of an infinite line is kind of useless if functionally it's either 0 or infinite, right? If it's any constant value throughout a thing other than the whole line other than 0, then the charge is infinite. So we're going to, instead of talking about in the end we're going to talk about linear charge densities, but I guess we'll talk about total charge for now. So I'm going to draw a Gaussian surface around this thing. So I like to draw my Gaussian surfaces as dashed lines. And there's the top. I'm going to draw a nice cylinder. And draw that bottom on there. Yeah, there we go. So now this is infinite, remember? So I don't actually really care about the end caps. So I mostly am going to care about the radius, right? So this is going to say have a radius here, r. Right, and so we're looking at the electric field on the surface of this Gaussian. So what I'm going to do is I'm going to go back to my Gauss's law. So once again, you can write it as flux equals EA and flux equals charge enclosed over epsilon naught. But I kind of just like to say EA, electric field times the area, is equal to just charge enclosed over epsilon naught straight away. So it's fine if you guys want to do that. So, I mean, we can easily just go ahead and say electric field is equal to charge enclosed over epsilon naught times the surface area, which is kind of an important thing to actually realize, that this area is the surface area, and that's why that electric fields go like 1 over r squared normally. From a point charge, it's expanding into 3D space like a sphere would expand. So it's going to depend on the area of a sphere. That's where that 1 over r squared comes from. Here, we're going to be not expanding like a sphere. We're going to be expanding like a cylinder, right? So what's the area of the cylinder, of the surface area of the cylinder? Once again, ignoring the end caps. So it's going to be the circumference, right, around times the height, or we're going to call it length. So we know that, let's write up here, area is equal to 2 pi r times the length, right? And so if we make this thing infinite, the end caps don't matter. I have an infinite length there, and I have an infinite charge, because my charge enclosed, is just going to be q, we'll say. So let's go ahead down here, and we're going to substitute in. So I'm going to say q over epsilon naught times 2 pi r L. I'll put that in parentheses just so you can see I substituted in. So yeah, I've got an infinite here, I've got an infinite here. But the nice thing here is that what we actually are going to do is we can, move this up so you can see what we're doing. That looks good. Say E, the electric field, is equal to your charge over 2 pi epsilon. Let's put those together. But this charge, I can say charge over L, right? I can do it like that and put my R down here. And we know that Q over L is equal to lambda, your linear charge density. So I'm actually going to write this guy in the end. My electric field is going to be lambda over 2 pi epsilon naught R. And that's my answer. All right, hope you guys enjoyed this one. And as always, like and subscribe. And if you want to get notifications every time I upload a video, hit that bell button. All right, I'll see you guys next time.